In this video, we will have the proof of Lemma 5.3.4 and Theorem 5.3.3. Now, this lemma states that there is an isomorphism tau double star from fx mod v onto f prime of t mod v prime, where v is generated by f of x and v prime is generated by f prime of t, with the property that it takes the base field, namely base field element alpha to alpha prime. So first we know that um, tau from f to f prime, if that is one-to-one onto homomorphism, we produced mapping tau star from fx to f prime of t, which is also one-to-one onto homomorphism. So this is known to us, and with the help of this only we are going to establish this. That is why we are mentioning this. Now we'll consider V to be an ideal generated by f of x. Then, you consider this, then V is an ideal of fx, and fx mod V is a ring. Unless f of x is irreducible, we cannot have this to be a field, so it is just a ring. Now, similarly, you consider V prime an ideal generated by f prime of t in capital F prime t, and you consider this one, which is definitely a ring. Now, you define, so what is this and what is this, we have said. Now, define tau double prime from this to this in this way. It takes any element, because any element here is of this form, and here any element is of this form. So what is this g prime of t? It is nothing but the image of g of x and tau star. So that is what this g prime of t is. This g prime of t is nothing but the image of g of x and tau star. Tau star we have already assumed. What is tau star? So now this being a rule defined by us, we are first proving that it is well defined, for which we consider two elements in the domain to be the same. You have your domain to be fx mod v, and you have your codomain to be f prime of t mod v prime. So from this to this, you are defining tau double star. So two elements in this must be equal, should imply the corresponding images in this to be equal. So that will give well definedness. And when you come from there to here, it will be your one-to-one. So well defined, first we are proving. So you consider h of x plus v equals g of x plus v, which in turn gives this. This we have been using. I used to say that in the case of groups, you have HA equals HB if and only if. This is a very famous result in group theory. So you have AB inverse. This is if and only if condition. Same thing here. Whenever you have quotient, you have this. Here h of x, AB inverse means here addition is the operation. So that means you will have A minus B. So that is what you have here. So h of x minus g of x belongs to V, and V being generated by f of x, you can write like this, and you are applying tau star because tau star is a mapping. So the elements in the domain equal means the images must be equal. So you have this tau star is a homomorphism, so you have this step both on the left and right side, addition, multiplication. So this in turn gives the image of this is h prime, and this the image of this is g prime, and this being written as a multiple of f prime of t, and v prime is generated by this, so naturally this element should belong to this. Again we use the same concept here to have this step, and this is nothing but the image of h of x plus v and a tau double star, and this is the image of g of x plus v and a tau double star. So this proves your well definedness of tau double star. For one-to-one, we'll consider the images to be the same, and we have to show that the pre-images are equal. H of x plus v should be equal to g of x plus v. So this is nothing but h dashed of h prime of t plus v prime, g prime of t plus v prime. So again the same concept, A B inverse, the same concept that's used here. So you have this to be h prime of t minus g prime of t belonging to v prime. Again, v prime generated by f prime of t, so you can write like this. And this in turn gives the image of h of x and a tau star, and similarly these steps that you have. And tau star is a homomorphism. Because tau star is a homomorphism, you have this step. This is because your v prime is generated by f prime. So that is the reason. So here tau star being a homomorphism, you have this step. So the tau star being 1 to 1, the pre-images must be equal. So you have this, but your v is generated by f of x. So you have this step. So the reason for this step is this. So this again in turn implies again same result is used. So you have this step. So tau double star is 1 to 1. Now to prove that tau double star is onto, so for that you consider an arbitrary element in the codomain where this one is a member of f prime of t, which means because tau star is onto, you can find one g of x in fx, so that you have this step. So you have the existence of g of x in fx is assured. So g of x plus v will act as the pre-image. So immediately you have your tau double star to be onto. Now to prove that it's a ring homomorphism, two elements in the domain are to be considered. That is, you have to consider g of x plus v plus h of x plus v, two elements in the domain, and you have to show that that is equal to this. But this is nothing but g of x plus h of x plus v. So proving this is same as proving this. So straight away it is written, but actually speaking this is to be written and then only this step. So similarly here also one more step is missing. G of x plus v into h of x plus v tau double star, that in turn gives this. So you have to establish this. So we'll consider the LHS of first and then the second. So this is what we have, and by the definition of tau double star, it is nothing but the image of this and a tau star plus v prime. But tau star is a homomorphism, so you have this step. And by the definition of addition in any quotient ring, you have this step by the definition of addition in quotient ring. By the definition of addition in any quotient ring. That is the reason. Whenever you write each and every step, try to write within bracket the reason for this step, so that when you try to prove any new, when you attempt to prove any new result, you will automatically write the steps. Because once you know that how each and every step comes, you will know it later when you want to prove anything on your own. So this is g of the image of g of x plus v and a tau double star, and this is image of h of x plus v and a tau double star. So that is your RHS. In the same way for the product also we have this. Tau star is a homomorphism, so you have this step. Again, by the definition of multiplication in any quotient ring, you have this step. And so we have got the images being separated. And so this is your RHS. And alpha tau double star is same as alpha tau star, but alpha tau, and that is same as alpha tau, and that is alpha prime. So since tau double star from this to this is 1 to 1 onto homomorphism, we conclude that fx mod v is isomorphic to f prime t mod v prime. So next we have this theorem, which is Theorem 5.3.3. Statement of that is, if v is a root of an irreducible polynomial, say p of x in fx, and w is the corresponding root in f prime of t, root of p prime of t in f prime of t, then f of v, what is f of v? By joining root of an irreducible polynomial. V is what? Root of irreducible polynomial. But we know that irreducible polynomials are minimal polynomials also. But so if that is the case, then your V becomes algebraic. If we know the degree of that polynomial, degree is also written algebraic of degree n or something like that. So this is what we have to establish. Under this isomorphism, we are asked to show that this V is taken to W and alpha is taken to alpha prime. So what is given first? We'll write that V be a root of the irreducible polynomial P of x. Then P of E is 0, named as equation 1. P of E is 0 is equation 1. And let V be the ideal generated by P of x. So this is irreducible, means V must be maximal. You can refer the last theorem in polynomial rings. So there we have mentioned this, given the proof also. So V is maximal in fx, and so this is a field. R by M is a field whenever M is maximal in R. R is commutative with unit element. So using that result, you have fx mod V to be a field. Now you define, see why this has to be brought in, because when we want to talk about f of v, we know pretty well that it is a field. So the concept of field somehow is to be brought in. So that is why all these steps are written. Now define your mapping psi from fx to f of v. See, this is written with in Hurston, this is written with square bracket, and this is written with ordinary parenthesis. Don't put I mean, if you know the actual meaning, but in some of the books they use for both collection of polynomials and extension field, everything the same notation. But as far as Hurston is concerned, he distinguishes between this and that. So this is with ordinary parenthesis, this is with square bracket. Now you define the mapping in this way for every f of x in this. Then the psi is a ring homomorphism. All this with the f of a we have established. Like your evaluation homomorphism. This is nothing but evaluation homomorphism, which you have studied in the previous sections. So psi is a ring homomorphism. Now kernel, when we consider, this is all those polynomials which are mapped onto the identity element of the codomain, namely 0. So this is what you have. And kernel is always an ideal. Kernel of homomorphism is always an ideal of the domain. So we shall name this as, say, some m. It can easily be seen that V equals m. This is what we have already established this. When we consider this m, kernel psi is m. Now we can easily see that this V is contained in m contained in fx. All this explanation already we have given in when we proved that A is algebraic if and only if f of A is finite extension. So in that we have established, but again we'll just see how first V is contained in m. Because you have your P of V. See, V is generated by P of x and P of E is 0. So all those polynomials which vanish at V, they should come under kernel. So you have, because kernel is defined in that way. So V is contained in M, and M being an ideal in fx, this relation that we have. But M is maximal, V is maximal. So you should have either V equals M or M equals fx. But in this you have 1, but that 1 does not belong to m. So you don't have this possibility, only v is equal to m. So v is nothing but your, in this case v is nothing but this, and m is this. So v must be equal to m. It can be easily seen that this. So by fundamental theorem on homomorphism, so what is that you have? You have your fx to f of v. This is an onto homomorphism with kernel. Not this is onto, this is just a homomorphism. But when you go to fx psi, it is onto. When you go to this, then it is fx, it is onto. With kernel, this one v, m you have taken, but that m is nothing but v. So fx mod v must be isomorphic to fx psi. And again, if you refer that theorem, f of a is finite extension if and only if a is algebraic. So there also we have established that how is that fx psi is equal to f of v. F of v contains fx psi obviously, and fx psi is contained in f of v. So because of those two you have this, all those things are established there itself. So just we are recalling and using that here. So fx psi is f of v. So what is that I have? I have my fx mod fx to f of v. We have a mapping which is homomorphism. But when we restrict that to fx psi, which is exactly f of v, we have that to be on to homomorphism with kernel v. So fx mod v must be isomorphic to f of v. So that isomorphism one-to-one onto isomorphic means we will have a one-to-one onto homomorphism between this and f of v. So that is taken as psi star. So how it takes elements, fx plus b takes any element to f of v for every fx plus b in fx mod v. And in this under this homomorphism, x plus v particularly will be taken to this, and alpha psi star is alpha. Now let w be a root of an irreducible polynomial p dash of t in f dash of t. Because p of x is irreducible, we proved in one of the proposition that this is also irreducible. And again the same procedure. What we did for v, we are going to do for v prime. Let v prime be generated by p prime of t, then v prime is maximal and f prime in f prime of t, and this is a field. So by the again same argument, you can have f prime of t mod v prime to be isomorphic to f prime w, defined by in this way. So for every element in the domain you have this, and particularly this t plus v prime will be taken to w. So you have alpha prime. This mapping is taken as theta star. So this is what we have. And we proved just now that tau double prime is a mapping between these two, and that is one-to-one onto homomorphism that is defined this way. Now you consider the image of x plus v and a tau double star. We proved that this is t plus v prime. And when you consider alpha tau double star, it is alpha prime, right? So what is that exactly that we need in this statement is f of v is isomorphic to f prime of w. So what is that we have so far is we have got psi, we have got theta star, and we have got tau double star. What are they? Psi is a mapping from fx mod v to f of v, and theta star is from f prime of t v prime to f dash of w, and this is from fx mod v to f prime t mod v prime. So we want to connect this and this, and these are the tools that we have. So how are we going to connect? So that is what is written next. Now because psi star is a bijective mapping which is also a homomorphism, we have its inverse from this to this also to be bijective and homomorphism. This is also bijective and homomorphism. So you take this as the first mapping, composite that with these two, so that you will have from here, see it goes like this. You have psi star. Oh, this is introduced as psi star or just psi star. So you have this to be psi star. This is psi star. So you have your psi star inverse to be from f of v to fx mod v. So from here to here that you are going, and this one helps you to go from here to this one, and this one takes you from this to f prime of w. So we consider the composition. So it is psi star inverse, then tau double star, and then theta star. So it takes you from f of v to f prime of w. And because all these are one-to-one onto homomorphism, composition of bijective mapping is bijective, homomorphism means homomorphism. So you have the whole lot, the sigma to be one-to-one onto and homomorphism. And in this, what is taken to what? So that is also needed. We have our job is to say that our v is taken to w under this, and alpha is taken to alpha prime. So that is what we need. So you consider v sigma. V sigma means v psi star inverse composition tau double star theta star. Now this is psi we know by the definition of composition of mapping. So we write. So v psi star inverse is nothing but under see what is psi star? It is from this one, x plus v is taken to v, which means v is taken to x plus v. So that is what you have. V is taken to x plus v, but tau double star takes x plus v to t plus v, and theta star takes t plus v to w. All these are by we have named them as equation 2, 6 and 4. So according to that you are having this. So v is taken to w. Alpha, when you consider, again the same concept. So you have alpha being taken to some alpha prime. And here just the same thing that you have to have when you have a and b to be roots of an irreducible polynomial. So that we will have in the next video. Thank you.